Exponents. Let's look at a very important operation on integers called exponents. We are familiar with this from school. Here's an example. 3 raised to 2. It means 3 times 3. So basically exponents is repeated multiplication. 3 raised to 5 would be 3 multiplied by itself 5 times, and so on. Let's look at some rules of exponents. So suppose I had 3 raised to 5 times 3 raised to 3. What would this become? This would be 3 times 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 3. This is 3 raised to 5. This is 3 raised to 3. And I'm multiplying 3 totally 8 times. So it's 3 raised to 8. Therefore, the rule I get is x raised to a into x raised to b is x raised to a plus b. There the 5 and the 3 added up to 8. 5 and the 3 added up to 8. So when I multiply numbers with the same base, I can add the exponents. Another such rule is x raised to a divided by x raised to b equal to x raised to a minus b. The proof is similar, I won't go into it. The third rule is x raised to a, the whole raised to b is x raised to a into b. The proof for this is also similar, but let's just do it. Let's take an example. 3 raised to 2, the whole thing raised to 4. What's 3 raised to 2? 3 raised to 2 is 3 times 3. So this is 3 times 3 raised to 4. Now what's 3 times 3 raised to 4? That's 3 times 3 multiplied by itself 4 times. So that's 3 times 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 3. Which is 3 multiplied by itself 8 times, which is 3 raised to 8. So we got 3 raised to 2, the whole raised to 4, equal to 3 raised to 2 times 4, which is 3 times 8. And that's how the proof goes. Let me reiterate this rule. It is x raised to a, the whole raised to b is x raised to ab. Let's go back to the rule for division. X raised to a divided by x raised to b is x raised to a minus b. What if I take a equal to b here? Let me take a equal to b. So then the left hand side becomes x raised to a upon x raised to a, which is 1. And the right hand side becomes x raised to a minus a, which is x raised to 0. So if this rule were true for all integers, then I would have to define x raised to 0 equal to 1. And that is just what I'll do now. So x raised to the power 0 is 1. This facilitates the use of this rule for any integers a and b. What about negative powers? What does x raised to minus a mean? Let's see what it means. I'll multiply it by x raised to a. I'll multiply it by x raised to a, and that gives me x raised to 0, because when bases are same I add the exponents, and that we just discovered is 1. So x raised to minus a into x raised to a is 1. That makes x raised to minus a equal 1 over x raised to a. That's my definition for negative exponents. If x is raised to a negative exponent, it is 1 over x raised to the positive of that negative. What about x raised to a times y raised to a? Here the power is the same, but the bases are different. So this is simply xy, the whole raised to a. That's easy to see. X raised to a is x times x times x, a times y times y times y, a times. So I can move around the multiplication. I can write it as xy, 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 a times, which is what gives me xy raised to a. I can just pair the x's and y's together, multiply them out, because there's an equal number of x's and y's, which gives me this rule. X raised to a times y raised to a is xy raised to a. Of course, the corresponding rule, x raised to a divided by y raised to a would be x by y the whole raised to a. So let's quickly go over what are called the laws of exponents. X raised to a into x raised to b. The bases are the same, the exponents can be different, is equal to x raised to a plus b. That means when you multiply two exponents with the same base, you add the exponents. Similarly, x raised to a divided by x raised to b is equal to x raised to a minus b. When you divide two exponents with the same base, you subtract the exponents. X raised to a the whole raised to b. When you raise a power to another power, then you multiply the powers. X raised to 0 is equal to 1. Anything raised to the power 0 is 1. That anything, of course, should be non-zero. X raised to minus a is equal to 1 over x raised to a. So anything raised to a negative exponent is equivalent to 1 upon that same thing raised to the positive of that negative exponent. So x raised to minus a is 1 over x raised to a. You use this rule to switch between negative and positive exponents. Now we change the base. X raised to a times y raised to a. The bases are different, but the exponents are same. In that case, you multiply the bases. So x raised to a times y raised to a is x times y raised to a. The base becomes x times y. Similarly, x raised to a divided by y raised to a is x divided by y raised to a. The base becomes x divided by y. All these rules have been derived a few minutes ago, and once we understand the derivation, one doesn't need to make those absurd mistakes which one tends to do if one has learnt without understanding. Okay, the first example, 3x raised to minus 2. So what is raised to minus 2? Remember that the exponent has the highest priority. So it goes with the thing nearest to it. So this is interpreted as 3 times x raised to minus 2. And this is not 3x raised to minus 2. It is not that. If I wanted to write 3x raised to minus 2, I would have to put the brackets as I have done here. Right. 3 stays as it is. X raised to minus 2 is the same as 1 over x raised to 2. A negative exponent becomes positive if you move everything down to the denominator. So this becomes 3 over x squared. That's our simplified answer. How about this? 2x4 times 4x squared. So I'll group the x's together and I'll group the constant terms together. 2x4 is 2 times x4 times 4 times x squared. So everything is being multiplied. I can rearrange. Becomes 2 times 4 times x4 times x squared. If I have a row of things being multiplied, I can move them around. So this becomes 8 and x raised to 4 times x raised to 2. Now that's easy. X raised to 4 times x raised to 2. Since the bases are the same, I can add the exponents. This becomes x raised to 4 plus 2, which becomes 8 x raised to 6. Slightly more complicated example. 2 raised to 3 times a times c times b cube over 4a square b c cube. So let's separate out things which are of the same base. So 2 cube over 4 are the constants times a over a square times b cube over b times c over c cube. 2 cube over 4 square. Over 4 is 2 cube over 2 square. A over a square becomes a raised to 1 over a square. B cube over b becomes b cube over b raised to 1. And c becomes c raised to 1 over c cube. I'm just writing everything with a power so that I can use the rules of exponents. Of course, there are much quicker ways of solving this, but just let's stick to the rules. So 2 cube divided by 2 square becomes 2 raised to 3 minus 2. This becomes a raised to 1 upon a raised to 2, that's a raised to 1 minus 2. This becomes b raised to 3 minus 1, and this becomes c raised to 1 minus 3. Which finally becomes 2 raised to 1, a raised to minus 1, b raised to 2, c raised to minus 2.
So let's leave the ones with the positive exponents in the numerator, and the ones with the negative exponents we'll move down. So this becomes 2b square over a raised to 1 c raised to 2, which is 2b square over ac square. So I just use the rules of exponents step by step. Of course, a quicker way to do it would be 2 cube and 4. 2 cube is 8, so I can cancel the 2 and 4 and I get a 2. A and a square I can cancel and I get an a in the denominator. B and b cube I can cancel, I get a b square in the numerator. And c and c cube I can cancel, I get a c square in the denominator. And I get my answer as 2b square over ac square, just as we did earlier. Second example, ab cube divided by 2a cube b, the whole raised to minus 2. Let's first simplify within the brackets and then we'll deal with the raised to minus 2. So I'll simplify ab cube over 2a cube b. So that's a upon, firstly there's a 1 over 2, that's the constant. Then there's an a over a cube and then there's a b cube over b. So 1 over 2 stays as it is. This becomes 1 over a square and this becomes b square. So the answer is b square over 2a square. And now this whole thing is raised to minus 2. So when something is raised to minus 2, firstly to get rid of the negative exponent, I reverse the numerator and denominator. So this can be written as 2a square over b square raised to 2. I've got rid of the negative exponent. And now I need to square everything. So that's 2 square a square square over b square square. And that can be completed as 4a raised to 4 divided by b raised to 4. That's your answer. 4a raised to 4 upon b raised to 4. So I simplified within the brackets first, then I got rid of the negative exponent, and then when I squared the entire thing, each term got squared separately. If x divided by a is 4, a divided by y is 6, a square is 9, and ab square is minus 8, then what is x plus 2y? So I need to find out what x and y are, and then I'll be able to figure out what's x plus 2y. Where do I find out where x and y are? X is given in terms of a, y is also given in terms of a. So if I were to find out a, I'd be done. I'm given that a square is equal to 9. Can I find a from this? Well, almost. Because unfortunately there are two numbers whose square is 9. So a could be minus 3 or 3. So I'm not really done because I can't explicitly say what a is. Let's see if there's some more information to work with. ab square is equal to minus 8. What can I say about b square? Well, I can't say what the value of b square is, but I can certainly say something very interesting about b square. B square has to be positive. Why is that? Well, firstly, b can't be 0 because then the product of a and b square cannot be negative 8. It would be 0. So we know that b is not 0. If b was negative, then its square would be positive because negative into negative is positive. Even if b was positive, b into b square would be positive. So no matter what b is, b can be anything, but b square is positive. Simply because negative into negative is positive and positive into positive is positive. So I know b square is positive. I also know a into b square is negative. That forces a to be negative. Because positive into negative is negative and positive into positive is positive. Now this is enough information. A is negative. And earlier we had found out that a was either minus 3 or 3. Here. So a must be minus 3. A is negative. Now with a equal to minus 3, I can pretty much find out x and y quickly and be done. X by a is equal to 4. So x by minus 3 is equal to 4. X is equal to minus 12.
a by y is equal to 6. That means minus 3 by y is equal to 6. So y is equal to minus 3 by 6 equal to minus half. Now you can quickly find x plus 2y and get the answer as D, minus 13. Another example of exponents. Find the value of the expression when x equal to 17, and there is some horrific expression. Okay, so let's deconstruct this expression. It's x cubed square upon x square square. I'll deal with the numerator first. So I have x raised to 3, the whole raised to 2. So that's a power of a power. I know the rule to decipher this. When a power is raised to another power, I multiply the powers. So this becomes x, I leave the x aside, x 3 times 2, which becomes x into x raised to 6. And x into x raised to 6 is actually x raised to 1 into x raised to 6, and I can add the exponents to get x raised to 7. So the numerator has become x raised to 7. What about the denominator? X cubed, x square square. Follow the same steps. I leave the x cube as it is. I have a power of a power, so I multiply the powers, and I get x cubed into x raised to 4. And now again, since the bases are the same and they're being multiplied, I add the exponents to get x raised to 3 plus 4 equal to x raised to 7. So the denominator has also become x raised to 7. So our expression simplifies to x raised to 7 over x raised to 7. Now x is 17. Is that important? Well, it's important in some way. Now, let's look at this expression again. What does this expression simplify to? Well, most of you will say 1. And most of you will be wrong. Because I haven't told you what x is. You'll say, so what? It's the same thing in the numerator and denominator. Well, it's not. Because if x was 0, you'd be in big trouble. Because you'd be dividing by 0. And that expression is undefined. 0 divided by 0 is, well, meaningless. 0 in the denominator has no meaning in mathematics. So you can't say what that answer is because it's not even a mathematical statement. However, if x was anything but 0, then we are in a good place, because if x is not 0, then you can divide out that number and get the answer as 1. So here we are given that x is 17, so we are in a good place. X is not 0, I can divide out and I get the answer 1. The answer is C. Evaluating exponents. Let's see what this means, right to left. Let's look at an example of one of the other operations we know. How do you evaluate 3 plus 4 plus 9? Do you first do 3 plus 4, 7, and then do the plus 9 to get 16? Or do you do 3 plus 4 plus 9? Do you first do the 4 plus 9, 13, and then do the 3 plus 13 to get 16? Well, it doesn't matter what you do because it's addition, and no matter which way you go about it, you get the same answer. So what's the big deal about this? Let's see what happens when I do subtraction. 3 minus 4 minus 9. So should I do the first two first? I'll get minus 1 minus 9, which is minus 10. 3 minus 4 minus 9, the same expression again, but I'll do the rightmost two first. So I'll get 3 minus 4 minus 9, which is minus 5. And 3 minus minus 5 is 8. So yeah, it does matter. When it's subtraction, it matters whether I go left to right or right to left. Do I do the leftmost subtraction first and move rightward? Or do I do the rightmost subtraction first and move leftward? So which is the right answer? Well, the right answer is minus 10, because the laws of mathematics are so ordained that you'd go left to right. Okay. Is there any reason to go left to right? No, you just have to be consistent. It's a convention. Subtraction goes left to right so that everyone who sees such an expression gets the same answer. You can't get different answers, there'll be chaos. So subtraction goes left to right. Remember that. Division also goes left to right. However, exponentiation goes right to left. Let me give you an example about that. So 2 raised to 2 raised to 3 goes right to left. That means I evaluate this first and then evaluate the next exponent. So this becomes 2 raised to 3, which is 8, and this becomes 2 raised to 8, that is, I think, 256. It does not go, this is the correct way, it does not go 2 raised to 2 raised to 3, it does not go 2 raised to 2, the whole raised to 3. This is 4 raised to 3, and that is 64. As you can see, they're different answers. And here's an example. What is the last digit of 3 raised to 3 raised to 3? So 3 raised to 3 raised to 3, you've just seen by the rule that it goes right to left. So this must be interpreted as 3 raised to 3 raised to 3, which is 3 raised to 27. So we want the last digit of 3 raised to 27. So I'm going to find the different powers of 3 and their last digits. 3 raised to 1, last digit is 3. 3 raised to 2, last digit is 9. 3 raised to 3, last digit is 7. 3 raised to 4, last digit is 1. How do I get the last digit? I just multiply 3 with the last digit of the previous power. 3 raised to 3 times 3, the last digit will only depend on 7. 7 times 3 is 21, its last digit is 1. 3 raised to 5, 3. 3 raised to 6, 3 times 3, 9. 3 raised to 7, 3 times 9, 27. So 7 is the last digit. 3 raised to 8, 3 times 7, 21. 1 is the last digit, and so on. So you can see that the last digits repeat after every 4. 3971, 3971, and so on. We want the last digit of 3 raised to 27. They repeat every 4. So I'll divide 27 by 4. I'll get 6 and a remainder of 3. So here's what I'll write 27 as. I'll write 27 as 6 times 4 plus 3. So 3 raised to 27 is 3 raised to 6 times 4 plus 3, which is 3 raised to 6 times 4 times 3 raised to 3. Powers are the same, I can break them up. Now 3 raised to 6 times 4 is 3 raised to 4, the whole raised to 6 times 3 raised to 3. 3 raised to 4 has the last digit of 1. So 3 raised to 4 raised to 6 will also have a last digit of 1 times 3 raised to 3. So 3 raised to 3 is what is left to decide the last digit. And the last digit of 3 raised to 3 is 7. 1 times 7 is 7. And my last digit is 7. D. Roots. Square roots. We're familiar with square roots and cube roots. Let's abstract this information and understand roots in general. So what is the square root? If 2 squared is 4, then the square root of 4 is 2. These are equivalent statements. If 5 squared is 25, this means the square root of 25 is 5. If 3 raised to 4 is 81, this means the fourth root of 81 is 3. That's the meaning of roots. You're inverting the operation. Here, you raise 3 to the 4th power, you get 81. You take the 4th root of 81, you get back 3. So obviously, if I raise x to the nth power, and then I take the nth root of that, I'll get back x. That's basically what we're doing. So that's obviously one rule. With some caveat, x should be positive. We'll see this later. So let's see how we can write roots differently. So one way is to write root x, cube root of x, fifth root of x, and so on. Right. But I'd like to write it differently using exponents so that the rules of exponents come through nicely. Well, this is how I'll do it. So if I have x raised to a and I raise it to 1 by a, then by the rules of exponents, I'll get x raised to a times 1 by a, x raised to 1 equal to x. I multiply the powers, a and a cancel, I get 1. So x raised to a raised to 1 by a is x. But by this rule here that I've just written, x raised to a and the eighth root is x. It's the same thing. So I have two equivalent statements. I have x raised to a raised to 1 by a is x. And by definition, I have x raised to a and then taking the eighth root is also x. So that means these two terms are equal. That is, x raised to a raised to 1 by a is equal to x raised to a root a. Just replacing x raised to a by some y, I get y raised to 1 by a is equal to eighth root of y. So here's a very useful notation, that the eighth root of y can be written as y raised to 1 by a. So I've got the root, which is supposed to be the inverse operation of exponents, as an exponent. It's itself an exponent, which is wonderful. All the laws of exponents now work with roots. That's the beauty of this rule.
So let's see some examples where we manipulate roots. We saw how perfect squares could be easily simplified. Now we look at numbers which aren't perfect squares. So root of 75. Well, the trick here is to look for a perfect square factor of 75. I know that 75 is 25 times 3. And I know that 25 is a perfect square, so I'll use that. So I'll rewrite root 75 as root of 25 times 3. And now I can write this as root 25 times root 3. And root 25 is nothing but 5. So I get 5 times root 3, which is 5 root 3. And I've simplified root 75. So what's the rule I used? I used the rule root of a times b is root of a times root of b. Is this a new rule? Not at all. This is actually a times b raised to half, which is the same as a raised to half, b raised to half. We know when the powers are the same and the bases are different, that the bases can be multiplied. So we know this rule as a raised to x into b raised to x is equal to ab raised to x. We've seen this rule in exponents. I'm just reversing the usage of the rule. I'm saying ab raised to x is a raised to x times b raised to x. And this is the most powerful rule when simplifying roots. Okay, root 18 plus root 72. There is no rule for adding roots. Do not make the mistake of writing root of 18 plus 72. This means you haven't understood roots at all. What you need to do is simplify each root individually. So root 18, again I look for a perfect square factor of 18, that is 9. So I can write this as 9 times 2, which becomes root 9 times root 2, which becomes 3 root 2, root 9 being 3. Let's simplify root 72. Similarly, what's a perfect square factor of 72? 36. 36 is 6 square. So I write it as 36 times 2, which becomes root 36 times root 2, which becomes 6 root 2. So now I have it. Root 18 is 3 root 2 plus root 72 is 6 root 2. And I can add the root 2s. I have 3 root 2 plus 6 root 2. That gives me a total of 9 root 2. That's my answer. How about multiplying roots? Root of 60 times root of 15. So remember the rule. A raised to x times b raised to x is ab raised to x. And these two are multiplied. This is actually 60 raised to half times 15 raised to half. So this can be written as 60 times 15 raised to half, which means it can be written as root of 60 times 15. What's 60 times 15? 60 times 15 is 900. So this is root of 900, and we know that answer is 30. Let's do it another way. Let's simplify each root separately. So let's simplify root 60 first. Root 60, what's a perfect square factor sitting in there? 4. 4 is the perfect square factor sitting in there. So I can write this as 4 into 15. So this becomes root 4 into root 15, which becomes 2 root 15. 15 doesn't have a perfect square factor sitting in it. So second one, root 15, stays root 15. I can't simplify it further. So let's multiply the two. So root 60 is 2 root 15 times root 15. Okay, what's root 15 times root 15? Well, by definition it's 15, because root 15 is the square root of 15. So this becomes 2 times 15, which is 30. So either way, we got our answer 30. How about dividing two roots? Root 28 divided by root 140. So again, we know that a raised to x upon b raised to x is the same as a by b raised to x. Here x is half. Both the numbers are raised to the power half. So 28 raised to half over 140 raised to half can be written as 28 over 140, the whole thing raised to half, which means 28 over 140, the square root of that. Let's simplify under the root sign. 14 goes twice, 14 goes 10 times, that 2 goes 5 times, so I get 1 over 5, which is root of 1 over root of 5, which is 1 over root 5. That's my answer. 1 over root 5. Of course, if I don't want the root in the denominator, I need to do something. So I can multiply the numerator and denominator by root 5. This is called rationalizing the denominator. So now root 5 times root 5 in the denominator becomes 5, and I have a root 5 in the numerator. This is another way of expressing the answer. This has a rational denominator. This doesn't. Often this is the preferred way of giving the answer.
Simplify the expression root 32 minus root 50 plus root 18 upon root 8. Okay, let's just take one of them. Let's see how we simplify root 32. So as the square root of 32, I know 32 does not have an exact square root. So I'll try to extract the best number in there, which is a square, because its square root is possible. Let's see what I mean by that. So I'll write root 32 as root 16 times 2. Why? Because I know that 16 has a good square root, 4. And now by the rules of exponents, which is the same as the rules of roots, I can write this as root 16 times root 2, which becomes 4 times root 2, which is 4 root 2. So root 32 is actually 4 root 2. How about root 50? I'm again trying to look for a nice square term inside 50. A factor of 50, which is a square. That factor is 25. So this will become 5 root 2. Because it becomes root 25 times root 2, which is 5 root 2. How about root 18? Look for a perfect square factor of 18. That's 9. So it's 9 times 2. So this becomes 3 root 2. How about root 8? Well, that factor is 4. 4 times 2, so it becomes 2 root 2. Now let's write all of these. So the question becomes 4 root 2 minus 5 root 2 plus 3 root 2 over 2 root 2. How do I add root 2's? Well, I add them like x's. Root 2 is a common entity. So it's 4 root 2 minus 5 root 2 plus 3 root 2. How many root 2's is there? That's 2 root 2. 4 minus 5 plus 3 root 2's. And that's 2 root 2's. Divided by 2 root 2, which is 1. Why is it 1? Because 2 root 2 is not equal to 0, and I can divide it out. So the answer is 1. C. Simplify the expression 1 minus root 3 over 1 plus root 3. Okay, what do we mean by simplify this expression? What we mean is that we have a root in the denominator which doesn't simplify. Root 3 is actually an irrational number. You can't express it in any neat form. It's a decimal expansion that goes on forever and ever. And I want to simplify that expression so that I don't have roots in the denominators. If at all there are roots, let them be in the numerator and let the denominators be clean. So that's what we mean by simplifying. So how do we go about it? Well, we need a few simple algebraic expressions. Let me write them down here. You're supposed to know these. A plus b into a minus b is a square minus b square. A plus b the whole square is a square plus b square plus 2ab, and a minus b the whole square is a square plus b square minus 2ab. These three common expressions involving squares are known as binomial entities because they involve a and b, two things which are raised to some powers. These three are all different. A plus b into a minus b, the answer is a difference of two squares, a square minus b square. While a plus b the whole square and a minus b the whole squares have a square and b square and a third term. Well, I have 1 plus root 3 in the denominator and I want to get rid of the root 3. So if there's a square root, the best way to get rid of it is to square the term. So let's square it. 1 plus root 3, if I square it, let's see what I get. So this is like a plus b the whole square. So I'll get 1 square plus root 3 square plus 2 into 1 into root 3. So I get 1 plus, what's root 3 square? That's root 3 into root 3, that's 3. Plus 3 plus 2 root 3. So I haven't got rid of my root term. I still have a root, 2 root 3. So obviously squaring a term like 1 plus root 3 will not help me. But what will? If I multiply 1 plus root 3 by 1 minus root 3, then this becomes a plus b into a minus b, which becomes 1 square minus root 3 square, which becomes 1 minus 3, which is minus 2, which is great because there's no roots now. So multiplying a term like 1 plus root 3 with 1 minus root 3 did it. Just squaring it didn't do it. And that's a very important thing to note. Let's get back to our expression. 1 minus root 3 over 1 plus root 3. So I know that I would multiply the denominator by 1 minus root 3. So I better multiply the numerator by 1 minus root 3 too. I can't just multiply a denominator, the expression changes. I got to multiply numerator and denominator by the same thing. So effectively I'm multiplying by 1 and I'm not changing anything. 1 minus root 3, 1 minus root 3. So the top becomes 1 minus root 3 the whole square. And the bottom becomes 1 square minus root 3 square, which simplifies to 1 square plus root 3 square minus 2 into 1 into root 3 over 1 minus 3, which again simplifies to 4 minus 2 root 3 over minus 2, which becomes minus 2 plus root 3. What we've done is called rationalizing the denominator. We cleared the denominator of roots of numbers that are not nice numbers, that is like root 3 or root 5 or root 7. Roots of primes typically do not have a nice closed form. They are decimal expansions that go on forever. They are called irrational numbers. We made the denominator rational by multiplying by something. Let's see some more fractional powers. P is 216 raised to minus 1/3 plus 243 raised to minus 2/5 plus 256 raised to minus 1/4. 216 raised to minus 1/3. What does raised to a negative power means? Raised to a negative power just means 1 over 216 raised to 1/3. And what does raised to 1/3 mean? We saw what that meant. It means the cube root of 216. It's the inverse operation of cubing, raising to 1/3. So it's taking the cube root. And the cube root of 216 is 6. You should know that. Similarly, 243 raised to minus 2 by 5. Reciprocate to get rid of the negative power. It becomes 243 raised to 2 by 5. 243 raised to 2 by 5. 2 by 5 is a composite fraction. It's actually 2 times 1 by 5. And that's how I'm going to write it. I'm going to write it as 243 raised to 1 by 5 and the whole thing raised to 2. Why did I choose it this way? Why didn't I write it 243 raised to 2 and the whole raised to 1/5? Both are the same because when a power is raised to a power, they get multiplied. So both would be 2/5. But there's a reason I broke it up this way. I know that the 5th root of 243 is 3. So this further simplifies to 3 raised to 2, which is 1 upon 9. So knowing the 5th root of 243, or knowing the powers of 3, the powers of 3 are 3, 9, 27, 81, 243, 729 and so on, is very useful. I could immediately figure out the 5th root of 243. How about 256 raised to minus 1/4? 256 raised to minus 1/4 is 1 over 256 raised to 1/4. And again, if your knowledge of powers is good, 256 is 2 raised to 8, which is the same as 4 raised to 4. So this becomes 4 raised to 4, the whole raised to 1/4, which is 1/4. Just showing you the steps. So we have all 3 fractions. Let's see what we can do with them. So P was 1/6 plus 1/9 plus 1/4. Let's take the LCM. 36 and add 6 plus 4 plus 9. That's 19 over 36. The question is strange. The question isn't what is P. The question, let's go back to it, is if P is this, then which of the following is an integer? And we got P as 19 over 36. We got P as 19 over 36. And which of the following is an integer? Look at A. A is P divided by 19. Well, obviously 19 over 36 divided by 19 is not going to be an integer. It's going to be 1 by 36. What about B? P by 36. 19 over 36 divided by 36 is going to be 19 over 36 square, which is again not an integer. C, P. Yeah, P is not an integer. I can see that. D, 19 over P. That's interesting. Let me work out 19 over P. That's 19 divided by 19 over 36, which is 19 times 36 over 19. When you divide by a fraction, it's equivalent to multiplying by the reciprocal of the fraction. The 19s can be divided out and I get 36. So that's my answer, D. D, 19 over 36 is an integer. Let's move on to the next example. The value of some horrific expression is how many times the value of 2 raised to minus 14. So the 2 raised to minus 14 gives me a clue. They want how many times the value of 2 raised to minus 14. So I will pull out 2 raised to minus 14 common. And what's left is how many times it is the value of 2 raised to minus 14. 2 raised to minus 14 plus 2 raised to minus 15 plus 2 raised to minus 16 plus 2 raised to minus 17. When we take 2 raised to minus 14 common, because all are powers of 2, I can take some power of 2 common. What's left is 1 plus. So recall the rule that whatever is left behind here, 2 raised to minus 1 times 2 raised to minus 14 should give 2 raised to minus 15. That's how it works. When I multiply back 2 raised to minus 14, I should get 2 raised to minus 15. So it must be 2 raised to minus 1 because I add the exponents. Plus 2 raised to minus 2 plus 2 raised to minus 3. Again check. 2 raised to minus 3 into 2 raised to minus 14 is 2 raised to minus 14 plus minus 3, which is minus 17. So I have 2 raised to minus 14 common, and this whole thing is divided by 5. That's the expression. So this part is the answer. That is how many times it is the value of 2 raised to minus 14. So let's work out the numerator of this expression. That's 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, which is easy enough. The LCM is 8, and I get 8 plus 4 plus 2 plus 1, that's 15 over 8. So the expression is 15 over 8, the whole thing divided by 5, which is 3 over 8. And that's my answer. 2 raised to minus 14 into 3 by 8 is the value of this entire expression. So what we are looking for is 3 by 8. C. So even though this expression was quite ghastly, the fact that the question said how many times the value of 2 raised to minus 14, I knew I had to extract 2 raised to minus 14 as a factor, and that made life really easy. Here's something most students trip up over, so let's just thrash it out right at the beginning. X square equal to 9 and x equal to root 9. Are they the same? What does it mean to ask the question, the solutions of the equation? It simply means that whatever values I put for x, will it make this statement true? So if I put 2 for x, I will get 2 square, which is 4, which is not equal to 9. So that means 2 is not a solution of this equation because the statement is not true. However, if I put 3 for x, then 3 square is 9 and the statement is true. 9 is equal to 9. I can also put minus 3 for x and I get minus 3 squared is 9. And again, 9 is equal to 9, so the statement is true. So minus 3 is also considered a solution. So the solutions of x are 3 and minus 3. How about this equation, x equal to root 9? What can I put for x to make it true? Well, unfortunately, the square root sign only permits positive answers. If I see a square root sign, I'm only allowed to take a positive answer. So for instance, square root of 4 is only 2, square root of 16 is only 4. The square root of 9 is only 3, and so on. So the only value of x that will make this statement true is 3. There's only one solution to x equal to root 9. However, there are two solutions to x square equal to 9. So the solutions are not equal. These two equations are not equivalent.